talk about the approach taken to non-commutative geometry, where we ask the question: what happens if you kind of only have partial information, so partial spectral information, and what kind of structures that gives rise to? So there's two aspects. One is spectral, and one is more like a spatial resolution. So on both sides, we come to a structure which is actually quite common for both of them. So here's an outline. So this structure is called operator systems, which it has nothing to do with computers. If you are familiar with that word, and maybe if you Google something, then I will give an example, a very concrete example, but also quite rich. In structural spectral truncations of the circle, it's like doing Fourier theory, but only with finitely many modes. And then one may wonder all kinds of things, whether it would converge to the circle, or what kind of structure do you actually get? Can you make sense of that? That sense will be given by Gromov-Hausdorff convergence, like using this metric on metric spaces. And then this other alternative kind of point of view, which is more spatial, spectral, so sort of dual, is when you take finite spatial resolution. But let's start with a sort of a gentle. I'm not going to give you the introduction to non-commutative geometry or spectral symbols. Still, it's 9 o'clock, so right away throwing all kinds of things at you. But this should be sort of familiar, maybe from last week. Otherwise, for decades. So, so this is sort of the idea that you try to capture geometry, so mainly spin geometry to be precise, by spectral data, so a C-star algebra, and an unbounded operator, which is the Dirac operator, and they kind of meet and act on a Hilbert space. Bounded, the other one unbounded. So it will not be so much about kind of analytical details for that today, because actually these truncations make it like the functional analysis very simple, finite dimension. Then so this is of course simple, and the idea is that you can talk about geometry, or at least metrics, by taking the distance between 2 points to be given by that formula. That's actually the remaining distance. So you can kind of reconstruct it from this set of data. And this is a. Be careful when you press something. So this thing here, it's the distance that you get between points, which is I usually illustrate it like this. So you measure points, the distance between 2 points x and y, by moving it into function space, so in the C-star algebra or some sub-algebra, where you kind of control the gradient of that function. So it should be not larger than 1, so that you can actually make that transfer from space to function space. And that formula will be kind of, I will just be imitating that. It's been around also for a long time, since the very beginning actually, to be able to reconstruct the distance, the remaining distance from this data. But it's of course much more general. And here's this more general approach. So this will be, of course, the non-commutative situation where you allow for C-star algebras A, which are possibly non-commutative, self-joint operators, B, compact resultant and bounded commutators that are kind of reflecting properties that you find in the commutative case, and they also meet in the space. So now the distance function also makes sense when you look at states of the C-star algebra. So I can look at the distance between two states, phi and psi, and the supremum, just imitating that function from the previous slide. So you take these states, evaluating them at A, and take the gradient, again controlled by this commutative bound. Then the pure states, which would be kind of the extreme points of this set of states, this compact set of states, that will be corresponding to the points I had before, and then evaluation at the point x and at y, that would be kind of using the formula that I'm showing now on the previous slide. So I get a distance function on the state space of A. And A will be, maybe I didn't say that, unital. That's some, these kind of nice controlled compact convex set. So you can talk about it extreme points without too much trouble. This is the generalized distance function, and this works for any C-star algebra A given such a data. Now, so there's this setup. So it's spectral. The spectra, C-star A operator on space B. Also a spectral ingredient. I mean, I just use spectral to kind of put together this idea of having something operator type. However, so you need to know all of that. So you need to know the full package. So if you think about the self-adjoint operator D, you have to know the full set of eigenvalues. You just need to specify this function. Maybe not solve it exactly, but you have to know the full operator in order to work with it and to actually reconstruct the space that you're looking at. And if you think about this in terms of physics, that's not very realistic because you typically have some kind of limitation in what you can measure, frequencies or bandwidth or energy ranges, resolution. So there's always this kind of limitation that you need to take into account. And so what we're trying to do is, motivated by this, is to develop what kind of mathematics is needed to do this kind of spectral noncommutative geometry when you only take part of the spectrum, or when you take the finite resolution into account. So this is what we're trying to set up, and there was some earlier work that's actually in line with this, but maybe put it in context. Then there was some work of Al Glaser with Abel Stern, which working in Nijmegen on computer simulations for spectral geometry. And also there you kind of limited by the fact that on a computer you also have to sort of truncate somehow. And this can be done nicely in analysis, but functional analysis, but then you're kind of you're doing this kind of spectral truncations. And there's two papers that I wrote with the Noncommutative on this. And it's still ongoing, where we kind of try to see more examples and more formalism. So on two sides of that. This you also see now. Okay, so slowly moving towards operator systems. So if you think about what you have is, so AHD, my spectral triple. If I truncate that, then I can, first of all, take some kind of, let's say, spectral projection for D. So you can kind of restrict to the range of that projection, so that's still in Hilbert space. PDP, which is just a restriction of this operator that just naturally acts there, so there's still a self-adjoint operator, so this is all fine. And the algebra, if you want that to act, then you find there is some issue, because it will actually end outside of P of H, typically, unless it's P of H be an A, but that's very unnatural. So if you try to force your algebra to act on this closed subspace, PH, so you compress it with P, then that's not an algebra anymore. So PAP is just what it is. If you take multiples of that, then you will not end in PAP. However, there's a crucial property, the structure that is still satisfied, is that it's an operator system. And an operator system, and I will give you all the definition in a moment, but it just means that I can take stars. So it's like it's a closed subspace of operators, which is closed onto the star. And so that is still there. And this allows me to actually talk about all the things that I've been doing in the previous slides for these operator systems. The fact that you have this star. And more about this I will also explain. There's another approach. If you take metric spaces with a finite resolution, and then I would just take the most kind of thing that comes to mind is you take two spaces x and y, and I want to sort of identify them when their distance is smaller than epsilon. But of course that's not a nice relation, or it is, depending on your point of view. It's not an equivalence relation, because this epsilon is fixed, so I want to fix my resolution, and I just have this kind of blurring or this possibility that I cannot distinguish these 2 points. But it is a tolerance relation, so which is just a reflexive and symmetric relation, but not necessarily transitive. So one has to deal with that. And now, what happens if you have an equivalence relation? Then you could say, well, let's associate the C-star algebra to the relation, which you are probably all familiar with. So it's essentially a groupoid C-star algebra that you associate. And it's really just integral operators which are supported on that relation. And So what happens is that if this is only a tolerance relation, I cannot take products because the convolution product will actually move me outside, actually make this epsilon like twice epsilon, etc. So I cannot take products, but since this is symmetric, I can still take the star. So this is if you take integral operators with that support on this relation, it's like it's essentially like you look at the relation as a subset of x plus x. You know, like in a band, taking the diagonal, and the integral operators are supported on there. The products you shouldn't take, but you can take the star, and this is another example of an operator system. So let's look at some more background on kind of the literature on operator systems, and so maybe this is the first definition in this generality of an operator system, also the abstract notion, but we mentioned that Arvidsson was way before, like 10 years before that, already working with these kind of function systems developing this theory. So you will meet in a moment. So this operator system, the complete version is just a closed vector space. Well, closed could be dropped, but star closed is the most important thing. And then bound operators, and it's unital if it contains the identity operator. And the structure, and this is actually driving me to the abstract definition of an operator system, which is very similar to C-star algebra. So you have this notion of C-star algebra as some kind of closed subalgebra of the bounded operators, but there is also the more abstract one. You can realize one by and the structure that is relevant is that if you talk about operators, and in particular if you have the star around, then you can talk about about positive operators. So there's a cone E plus of positive operators, where an operator is just positive if it's positive as an operator. There's this notion of a cone inside. And in fact, the structure that one should look at for operator systems is the matrix ordering. Because actually you can sort of amplify E into n by n matrices with values in E. And that would act on n copies of H on my Hilbert space. And then I can still view them as operators there and also talk about positive operators there. And that's this cone n and E plus. So I have all kinds of matrix cones that are sitting in this M and E that are playing the kind of the crucial role for the structure of the operator system. And then the maps that you should consider between operator systems are completely positive maps, where that means that so positive is just the positive E plus to F plus. Completely positive means it extends, this map extends to M and E, and then it also maps the positive and an F plus. So these are all positive. And isomorphism are then complete polar isomorphisms, which mean they really kind of identify the order structure in the sense that it's bijective and the inverse are completely positive. So that's the right notion of maps, and it's also something that is necessary to have at least some structure, because you may wonder, well, this is not very much. It's a vector space with a star. And I was talking about C-star algebras before, where I write an algebra structure. But you actually realize that this kind of notion of morphism, so working in this category, is actually the right one, because if you would restrict this or consider C-star algebras in this context, then complete order isomorphisms would actually be just isomorphisms of C-star algebras. So that's really the right notion to consider. So this positivity will play a crucial role, and also in kind of characterizing operator systems in a more abstract. Okay, so here's Arvidsson. So there was already a lot of work in the 60s on this. Also this idea that if you have an operator system, then it may be interesting to kind of associate a C-star algebra to it. Maybe the smallest or the largest, and anything universal that you may think about. So it's C-star envelope, I use that word, and some others may use it differently, but for the smallest also. So, so the C-star envelope is the smallest C-star algebra that is kind of generated by the operator system. And it may sound strange because my operator system was already somewhere represented somewhere. but it actually turns out that you can represent it differently, let it act in a Hilbert space in the same way, but on a in a completely order isomorphic way. And then still the seed algebra may be different, and this is actually what we're after. So there may be different realizations of my operator systems, for which the seed algebra that is generated may be different. So let me actually say this more precisely. So a Caesar extension of the unital operator system E, that's actually given by a Caesar algebra A, which it generates and a map into it. So that Caesar is generated by this kappa by the images of A. Then the Caesar envelope would be the smallest one in this sense. So so it will be this A, and any other B, any other Caesar extension would surject onto A. So that's really what's going on. So in that sense, you have to take like quotients. So in that sense, smallest. That's what we're after. Because otherwise, it may very much depend on the realization of the operating system. Yeah.
Question about the previous slide. Sorry, you said that complete order isomorphisms, when you apply to Caesar algebras, they just become isomorphisms in Caesar algebras. Do completely positive maps restrict to star morphisms, or it's not that nice?
Actually, there's a lot of room for maps which do not have that property, which are even used in approximations of Caesar algebras.
Right, okay, yeah.
Maybe that helps. Okay, so this is the notion of the Caesar envelope that one may So to make this more concrete, because these kind of universal objects are difficult to find, actually there's a very nice way, a nice approach to this, which I mentioned I think on the previous slide. This is work of Hamana, but it was also iterated a little bit, and it was not the kind of the approach that Arvidsson was thinking of. And actually that was realized only later in work of Davidson and Matthew Kennedy. The idea is the following. So how to find a Caesar envelope? Well, the idea is just to first take a Caesar extension and try to find that quotient. So I need to kind of surject. So, and it turns out that you can always do that for any Caesar extension. So the idea is the following. So you take a Caesar extension. The boundary ideal is kind of what you can throw away in the Caesar extension without losing too much information on my operator system. So here is the quotient map of A by the ideal, A by I. And it's completely isometric on the image kappa E inside A. So that means that I'm not losing much information on this operator system by taking that quotient. So you can get rid of it and you get another Caesar extension, which is smaller. Usually a boundary ideal is then the largest of those ideals. Now what happens is that if you take a Caesar extension, just any one you like, or a convenient one, then there exists a Shilov boundary ideal J that realizes the Caesar envelope by taking the quotient. And this is very nice because it means that you can take, so the typical situation will be Caesar algebra A, of which you know the ideal spectrum, and then you actually look in that spectrum, or maybe it's even empty or trivial. Then you're actually quickly done. Then you find that the Shilov ideal is already at the Caesar envelope. But maybe a good example, which is more in the sense of Arvidsson, is that they take harmonic functions on the closed disk. So I'm working inside the Caesar algebra continuous functions on the closed disk. But then I restrict to the operator system of harmonic functions. And of course, if you multiply harmonic functions, they will not be harmonic. So that's an honest operator system. But then you realize that actually, well, the restriction to the boundary, so you know from, I don't know which course, but typically with this treated somewhere, creatively maybe, is that you can restrict to the boundary and you know that the supremum will be attained at the boundary, supremum of the modulus. And that means that I can actually throw away all of the interior. So I can quotient out C0 of the open disk, D, without losing any information. And this means that the Shilov boundary, I mean, so this is like the dual version. is S1, which means that the C-star envelope is C of S1. The ideal is C0 of the open loop. So that's actually that's a completely different, well, I mean, it's a different seed structure than what I started with, the one which may appear natural, which was this closed disk. You see that this restriction map is actually it's somewhat better, so that's where you should represent this operator system. Now we'll come back to this example because actually this is, of course, related to all kinds of methods in create theory. So there is a measure that we introduced of how far away an operator system is from a C-star algebra. It's called a propagation number, prop E. And it's like what you get when you take like products up to order n, like polynomials, in my operator system, and then find out when that's a C-star algebra. And the smallest n we call the propagation number, and of course this we do in this universal C-star envelope. And so, for instance, for the harmonic functions on the disk, the propagation number is equal to 1.
In general, the propagation number can be infinite, right?
Yeah, sure. Yeah. We allow that to happen. So maybe so this is in the paper we need to put this phrase. Yeah, thanks. Yeah, so maybe about these harmonic functions, because it's a nice example. So this fact means that actually the harmonic functions in a sense are the same as C of S1. So it's actually already the C-star algebra, which may sound a bit strange because it's not like that. But the idea is that the restriction map to the boundary can of course be inverted by a Poisson kernel. So there's actually a one-to-one correspondence, which is not respecting products. That's not necessary. Because if you have this property that a harmonic function on a closed disk is just determined by the boundary value, by this argument. So that's a nice example where you see this in action. Even though this so it would put a different product structure on harmonic functions in a sense, coming from the boundary value and then going back and forth with something else. So we show that this propagation number is invariant under complete order isomorphisms. That's not too surprising, but also under stable equivalence, stable isomorphisms, so tensoring with the compacts. And this was later then realized, picked up, that it was the same as Morita equivalence for operator systems, but that notion was not around yet. There is now a notion. Nefterakis, Kakarialis, and Todorov that invented this, developed this. The previous work was on operator spaces and operator systems, and then it's actually the same as stable isomorphism. So that's very nice, and here I was a project the master student of mine worked on. The tensor product behaves as you would expect. You see already the entrance of non-unital here, so this is always something to keep in mind. So it's slightly more complicated, but the theory that we developed was actually geared to this non-unital case, which is rather subtle. So it's something I will not spend too much time on, but it's actually making the story much longer than what you see here. The idea of operator systems, which was kind of attractive for us, is that you can talk about state spaces. So positivity is ground, so I can talk about positive linear functionals, normal 1. And in finite dimensional case, it's actually a very nice duality that you can investigate. A dual operator system, which is the dual vector space with the induced dual cone. All kinds of usual properties, but the idea is that you can analyze the pure states on E by looking at the dual system and understand the extreme rays. So if you have a good understanding of the dual, then you have a good understanding of the state space. So this is what we use a lot to find this duality and to find the dual system. And this I will do for of the circle. So let's look at an example. It's a very simple example, but very rich in structure. So we look at Fourier theory. So it's a Fourier modes EK, and I want to truncate that Fourier in Hilbert space. We get these orthogonal projections onto the span of the first n Fourier modes with eigenvectors of D in this case. And I compress, and what I get is first of all, it's an operator system, but that's the general argument. But it's actually a very nice one because they are Toeplitz matrices, finite sized. So what I get is I get matrices. So first of all, if you act with a function like some e to the I t or whatever on my open space, it acts as a shift operator. That's why you get these kind of constants in the diagonal, the modes. But then it's truncated, so these diagonals get adjusted into n by n matrix like this. And actually, what you can show is that that you generate mn of c, and this you can actually do very explicitly. There's a formula for the matrix coefficient EKL in terms of products, actually, sums of products of Toeplitz matrices. And that's independent of n. You can just show by this that the propagation number is 2. And actually, this is the C-star envelope because mn of c doesn't have any ideals. So that's already very convenient. So you don't have to worry about the Shilov boundary ideal. So that's what I was trying to say before. But you have this notion of a C-star envelope already in place, which is actually quite different from the C-star algebra I started with, which is C of S1. So that's also something which is quite intriguing. So this propagation number is 2. It is just something to, which is an interesting property. And a dual operator system, which we call the Fejér-Riesz operator system. This is some other truncation. We take C star of Z, so you work in Fourier space with the convolution product. And then you just truncate at n. So you just take these kind of things, you have a support constraint in Fourier. And of course, if you take convolution products, that will grow. So you shouldn't take convolution products, or you cannot. Because then you will move outside of the C star of Z, n. So this is the notation. So I have this support condition, but it's symmetric, so I still have the star in place. And I say that an element is positive if it's positive in C star of Z or as a function of an S1 given by this Fourier transform. So here's an example where the propagation number is actually infinite, because if I do take products, this support will grow, and it will grow, well, it will eventually you get to C star of Z. So that's an example where the propagation number is infinite. So it's completely different from the previous one. And actually, we were trying to compare operator systems which look similar, find some duality or some word equivalence actually, but it just didn't work. And then we just showed that the propagation number was different, so that's rather helpful. So what is nice is that we can identify the extreme rays in here as elements A, which, and that's a very kind of, that's a property that you can check on these AKs where these zeros are all on S1. So in other words, I just have to pick the zeros on S1, a certain number of it, n. So the ratio is to have these zeros at on S1. This amounts to choosing those zeros on S1. The pure state. So here's the usual argument: is that C star of Zn is a sub operator system inside C star of Z. So I can extend the pure state to a pure state of C of S1, which are points of S1. That's to check that I get all of them. And this is possible by some kind of invariance. Where the nice thing is that if you do this kind of truncations, both this one and the previous one, you have S1 invariant. So the symmetry that I started with of S1 is still in place, even though I'm in finite dimensional systems. Because if you would do like finite Fourier theory, you reduce the symmetry from a continuous one to a discrete one, which is losing a lot of kind of structure in that passage. But here you still have that. And that's actually why you get all of S1, because of this invariance. Okay, so here are the guys involved. I mean, this is 100 years ago. So. And so here's Riesz. This is Fejér, and here's Theodori. He will also come back in a moment. But this was the 1910s, so where many results of this style were already done, but not in this context, of course. And in particular for this duality that I'm after, so there's a duality in the sense that there's a pairing which completely respects the order structure. So one will actually imply the order structure that I was given before, so that the functionals which are kind of given by this pairing will be positive if they're actually positive inside the operator system. And this extends to the complete order as well. Now that was actually picked up by Douglas Frederick. So we cheated in a sense by doing only the order structure, and Douglas Frederick we proved that using then actually the operator valued Fejér-Riesz lemma to prove it for the complete order structure. So Fejér and Riesz had this lemma where you can, so the idea is that you have a function which has a certain support on, like this actually, support like n, size n, so it goes minus n to n, and that function is a positive function when you look at it as a function on the circle, so as I'm doing here. Then the Fejér-Riesz lemma tells me that I can take a square root of that function. Now, you could always take a square root maybe by some C-star functional calculus, but here I want to take a square root which has smaller support, like half the size. And this is actually possible by the lemma. So he showed, or they showed, that you can take a square, so you can write a positive function with a certain support condition as an absolute value squared of a function with half the support. And that was crucial in proving this positivity, because it allows me to relate between the size n matrices that I have here and the support, which is actually much larger from minus n to n. In any case, it's nice to kind of have this lemma appear in this context. What it allows me to do is that the extreme rays correspond to the pure states on the other side in the dual system, which I just said were just points in S1. So the extreme rays in the positive Toeplitz matrices are actually labeled by these points, lambda. The pure state space is now also given by these n points that I had to choose for the zeros of the polynomial, 1 and S1. So this is just choosing n, which is points in an n torus up to permutation. So you like the n points on the circle up to permutation. And that's actually quite useful. And so one thing is that we could kind of re-establish a theorem of Pelletier-Odori, which said that if you take the Toeplitz matrix, then it's positive, even though if it can be written as this kind of positive combination of these kind of, what I was labeling with lambda before, for these kind of matrices. In any case, it's labeled by these points in S1. So its odd result phrased in this general. The spectral truncations then, so for n is equal to 3. The structure is already quite intricate. It's so this is just the 3 over 3 Toeplitz, the first kind of interesting situation. Then you find that the states, they are given by these vector states, labeled by x and y, 2 points on the circle up to permutation. And here is an illustration that we found for this projecting on 2 parts of that, for this pure state space. Actually, when you think about it, this is just a Möbius strip. So it's already quite some structure that you find in this state space, even in this simple case, of just 3 by 3 matrices. But that n is equal to 3 now the other direction, so large n. So that's where I invoke this Hausdorff convergence and also kind of related to other works on quantum metric spaces. So this is what I did directly after that, is that you could ask the question is, can you somehow let these state spaces that are now analyzed with the distance that you get from this kind of restricted Dirac operator on the circle, and you actually compare it to the circle itself. And so what you have to do for that is so Gromov-Hausdorff convergence is, or distance is about talking 2 metric spaces close to one another. So you have to talk 1 epsilon to the next and the other way around. So this is, it's kind of important to go back and forth So what I have, the first natural map is of course this Rn, which is given by this compression, just putting Pn on both sides. And that's a very nice one because it's positive, it's completely positive. So it behaves well with states. And of course, that's why we're looking at these kind of maps. So that's allowed me to pull back states that I have on C of S1n to the circle and maybe look at them there and see what they are. But I have to get the inverse as well, and that's much more difficult because I cannot just take that matrix with these kind of PA coefficients and take it positive as a matrix and then write these fill out these coefficients and write the function corresponding to that. But that map will not be positive. It will not be a positive function. Because the order structure is completely different. So I have to do something slightly more advanced. I have to sort of understand how to get from this Toeplitz matrix to a function on S1. Well, this you can do. And this I will not spell out, but the main point which I will kind of want to stress is that if you compose the restriction with going back, so what it actually does is that this map Sn is taking the convolution product with the Fejér kernel, which also had that support condition. And that is actually positive, and also completely positive. And the other way around, that's Schur multiplication. So that's sort of another somewhat complicated thing that you can do with matrices. You just like pointwise multiplication on the matrix entries. That's what this symbol indicates. So this is what we have to analyze, and this is the picture of the shape, but it's just indicating that you can. So here's some pictures that you just illustrate what these distances actually are when you compare them. So for that you need some estimates, and actually some Lipschitz control, which is what I call the C1 approximate inverse. So you have to control how they are kind of approximately each other's inverse by the Lipschitz norm, because that plays a crucial role in this distance. This is the formula I showed you before. And here are some computer simulations that tell me that indeed this distance will go to the triangle that we know for the distance, and these bands are these gamma ends that are found analytically. This is just merely an illustration. So this is to recall from Hausdorff convergence. Where the Hausdorff numbers are. I shouldn't really be talking about that. No, so it's about what I said. It's about talking one space close to the absolute neighborhood of, or inside the absolute neighborhood of another one, and the other way around, and then take the smallest such epsilon for all possible embeddings that you make. And here there's a notion where you try to put it into a metric space which has a metric that bridges these two metrics on the two state spaces. If you find that, then you can kind of do actually this kind of Hausdorff convergence. This we found with precisely the formula I showed you before. It will allow me to find such a bridge. And then you show, then you can show that the state spaces actually converge to the state spaces on the circle. And these are the probability measures on the circle. Okay, so that's all the states. Then Maria Heckelman, she showed that if you take the pure state spaces at the finite size level, and that actually also converges to the same state spaces of Suijlekom. So all the Borel probability measures. So you cannot really converge to points in a sense, but you always have this smearing effect. And it's actually a nice illustration of all kinds of possible sequences that converge to this object. Okay, here's a general thing which is mainly for Malte to pick it up later today. Is that there's the general principle of C1 approximate order isomorphism, which is that these maps that go back and forth, positive and so on, that should have to satisfy Lipschitz contractive, so that you control with Lipschitz law, and there's this approximate inverse also controlled by Lipschitz. And the examples that actually fit in this framework are what I just said: cubic truncations of Fejér-Riesz, which is like doing Fourier theory on a torus, but you just take kind of box truncations. So it's like a tensor product of circles. Fuzzy spheres, but of course done way before this. And that's actually initiating this whole line of reasoning. Also, quantum fuzzy spheres fit in the framework, but of course showed independently and before. All of these Fejér truncations that I showed you were generalized by default. They also showed that it converges to the system. And then later we will talk about the spectral truncations of tori in the top of the model line. Okay, so I have still some time for cases at finite spatial resolution. This is other thing. But if there are questions, by the way, so this is kind of a turning point. I'm sure this is your files suggestion afterwards. Okay, so let's look at the other case for which we also developed some general framework, but make it very concrete in a moment. So we look at the groupoids, locally compact, so quite general context. And you take what we call a bond, which is like this neighborhood of the diagonal in a pair groupoid. So this is what you should be thinking about. And later on, this will be very complete for the pair groupoids. So you take some subset that contains indeed units, but it's symmetric. So that's kind of this analog of tolerance relation. And if you have such a situation, an omega and a G, and I take the Hausdorff system by the way, then you can think about what happens in this construction of the C-star algebra, groupoid C-star algebra, by restricting to this omega. So the support of these integral kernels, which are compactly supported and continues to be like that, then that's actually an operator system. This is what we will be calling E of omega. So that's my operator system of interest. So if you think about Z, then you already saw that example where I restrict to the interval minus n to n. And then I'm just taking C star Z, so the group C star algebra, and inside that I have my Fejér-Riesz operator system. You could also take the cyclic group and also having some kind of support condition there. And then you get a completely different situation. You get the banded m by m circular matrices. So C star Cm, they will be circular matrices. And the support condition means that they're kind of supported around the diagonal by a band. So they're different, even though these omega n's are the same. So it's somewhat the ambient groupoid or group is actually important. Another possibility is to take a finite set, and you take a band, Rn, run the diagonal of a certain bandwidth, then you get just banded. And this actually will be a crucial example because it will allow me to understand the general case of this tolerance relation, because it will be of that type. Okay, so take a set X and a relation. So you may forget about groupoids if you are not comfortable with that. So you just take a relation R, X plus X, and if you are, then this is the pair groupoid. It's reflexive, symmetric, but not necessarily transitive. And of course, my example would be to take points X and Y in X, for which the distance is smaller than epsilon, for a fixed epsilon. That's my relation. I want to sort of identify these points, but I also realize that it's not an equivalence relation. So I shouldn't take the C-star algebra. Actually, if you know what I'm talking about, then these are the compact operators. But that's not a very good thing to discuss. It doesn't give me much information about X itself, because it will always be the same C-star algebra. So the obtained operator system is the closure of the integral operators with the support condition. And we see that it's indeed contained in the compacts, but it may be small. So let's look at some simple cases, finite sets, which is like the one I had before. So you take a relation R, X plus X, and suppose, I mean, that's maybe behind the scene that R generates the full equivalence relation. So you can compose, you get the full equivalence plus X. And it's nice to think about this in terms of graphs. So the relation is, of course, a graph when you have an edge, when there is actually, when the 2 points are in the relation as a subset of X plus X. So this means that if you look at the equivalence relation that is generated by R, then that's just saying something about the graph being connected. Being able to move through the graph, finding edges to go from one point to the other. The C-star envelope of this ER in this case is then the compacts on L2 of X, but that's just matrices, so it's finite size matrices. The propagation number is actually just this. The graphs is the diameter of the graph. You have to measure with length 1 every time how long it takes to go from any point to another point. That's the diameter. And then there's a situation where you have a chordal graph, so it's a special case of graphs. Then you actually can characterize the dual in terms of a positivity, which is different from the positivity I started with. So here, a matrix that is supported on R, so it's in my operating system, it's positive if it's positive as a matrix. But the dual will have something different. It's more like a quotient. It's not like an injection into MX of C. The dual would be a quotient. That's exactly what this order structure is. It's telling me that that is partially positive. So it's a partially defined matrix, which is not zero everywhere else, but put some numbers in that matrix on the places it's not specified, which makes it a positive matrix. That often exists and has been studied for this notion of chordal graph, which allows me to actually characterize the dual as a vector space. And that's, so here you see the kind of the tension or the relation between the abstract operator system, which is defined by this duality, and the concrete one, and you want to realize it as operators on a Hilbert space. That may be not so trivial to get, because the dual order structure may be not the one that you kind of is the most natural one if you let them act as matrices. Just of course as vector spaces, that's just the same thing. Being in a finite dimensional case. So the pure states of ER, since I'm in the compact operators, I know the states, the pure states of the compact operators very well. They're vector states. The physicists would just call these states. So they're vector states, and I just have to figure out which of these vector states restrict to pure states. And so what happens now is that it may turn out that the vector state has some kind of, if you write down the vector, there may be some gaps which are like 0. And then if you have this support constraint on my matrix, which is like a band, and it may happen that it would just kind of not be able to move from one block to the next one because there are these zeros. And then it would actually turn out that this vector with that property would fall into 2 pieces, and there would be 2 pure states, and or 2 states. And so this is what we call R-connected. So the relation should be able to move the support of the vector, the function on X, say from one to the other. So if you look at the relation R and you restrict it to the support, it should kind of get the full equivalent relation. And so here's an example where you really have these band matrices in place, propagation number, and the dual operator system is also band matrices. A trivial example of it. So what we apply it to is this this case of R epsilon. So that's a continuous situation, but we need some properties on X, of course. So the measure should have some compatibility with the metric. So it's we take a metric measure space with a measure of full support. So there's no like blocks which we leave out in X when taking the viewpoint with the integral operators. And we look at this this relation, and then you find that that under these conditions, so it's a little bit fast over this, but it's also not too important for the main point. That the C-star envelope of E or epsilon, they're the compact operators. The propagation number is actually the diameter of X divided by epsilon. And how many times you have to take this product to move the support to get to all of X. And the pure states, again, are given by these vector states, but now in the infinite dimensional case, where the essential support of psi is now epsilon connected. And the idea to analyze this is, well, maybe first the problem. So the problem is that this is a non-unital situation. So I didn't mention it really, but you felt it by talking about the compact operators. If you talk about states, and pure states in particular, you have to be a little bit careful, because these...
Do you assume that X has finite diameter?
No, not necessarily. If it's not, then it's infinite.
Yeah, but then, I mean, for instance, you have this rho algebra, which is smaller than all compact. Ah, okay.
So this is inside the...
Okay, yeah.
So this thing would fit inside there. The rho algebra is larger.
Sorry.
But there's a nice relation, because it's very much like that. So this support will actually tell me the propagation for the rho algebra. So it's really compatible. Yes, okay, the seed algebra is not interesting in that sense here. You really should be talking about this operator system with this condition. And then it's actually very much like the filtration that you find in the rho algebra. Filtration where you pick a fixed size, fixed propagation. Yeah, so to talk about pure states in this context is somewhat more difficult, because of the fact that this is not unital, but one can talk about an approximate unit. And for Caesar algebras, it's clear what to do. You take approximate identities, for instance. But here I have to talk about approximate units or something like that for operator systems. But I do not have a product. So what I have to do, and that's all underlying this result, is that I have to take an approximate order unit, which is something like behaves like a unit. It's like with Caesar algebras, which allows me to kind of relate the norm of my operator to the order structure that I have. And this is actually possible. And such an order unit that we found here, which lies in E of R epsilon, but it's an order unit for the compact. That is actually driving why we can talk about pure states even in this context. So we go via quasi-states, so norm smaller or equal to 1, that would be a compact set, compact complex. That will have 3 points, but we have to really kind of be careful. And that's all underlying this result. But I invite you to take a look at that paper, or we can talk about that. Not at this point, also given the time. So actually, the outlook would be to have more general or more more examples or more cases of examples which could be studied. So maybe compact Lie groups. Tori, we'll see in a moment how far we can get there. Bonds in groupoids are also kind of open for study, so it's not so clear whether that would have approximate order units or what the duality would be. The metric structure is still kind of somewhat open for these finite resolutions, and all the questions can be asked, and the final one would be like a general theory of spectral in the category of operator system. But I will stop and thank you for your time.